So in the last lecture, we have seen the interval minus pi to pi. We have checked the function, whether the function is even or not. But we have seen that the function was neither even nor odd. And now let's have some more example based on this interval minus pi to pi. Okay, so let us consider the example based on this interval. Okay, so let us find the Fourier series. So we'll go for the example. Find the Fourier series expansion of f of x is equal to x square in minus pi to pi. So we go with the solution like f of x is equal to x square p. We find in minus pi to pi with period pi. So we have L is equal to 2 pi and hence L is equal to pi. Okay. Now, as the interval is minus pi to pi, we need to check whether this is even function or odd function. So, you are supposed to identify this function directly. Okay, but for understanding, we'll check here. Then consider f of minus x. So it will be minus x bracket square. And we know this is going to be x square, so this is f of x. So what we get here, we get f of minus x is equal to f of x. And once you have f of minus x is equal to f of x, so we can say f of x is an even function. So this is a even function, and hence what we can say is we can say Bn is equal to 0. That when there will be even function, okay, then it implies that Bn is going to be 0. And now once we know that Bn is equal to 0, so we are able to write down the Fourier series for this, and hence we can write the Fourier series expansion of f of x is given as, what you can have is f of x is equal to a0 plus summation n running from 1 to infinity an cos of an x, let it equation 1, where now we have to be careful. Okay, see the formula number 5 which says that f of x is even and bn is equal to 0, the interval is minus pi to pi. So here we get a0 is equal to 1 upon pi integral 0 to pi f of x dx, and we have an is equal to, so an is 2 upon pi integral 0 to pi f of x cos of nx dx. Again, so these are the formulae that we have. Now let us evaluate this one by one. So first we consider a0, so 1 upon pi integral 0 to pi x square dx, 1 upon pi, then the integral will be x cube by 3 and 0 to pi. So we have 1 upon pi, then this will become pi cube by 3 minus 0. So I'll be having 1 upon pi and this is pi cube by 3. So 1 pi you can get cancelled and you'll be having a0 is equal to pi square by 3. So here we get this a0 is equal to pi square by 3. And so this is our equation 2. Okay, now we got a0. Let us find out what is an. So let's go for an now. Okay, and hence we have an is equal to 2 upon pi 0 to pi x square cos of nx dx. Okay, so here this is going to be u and this is going to be v. So we have to use generalized by parts rule. So we can say using generalized by parts rule we get. So what we are able to get is, see here we have an equal to 2 upon pi remains as it is. So first term as it is, integration of second. So it is going to be sine of nx upon n minus the derivative of this term. So 2x, then the integration of second term. So minus cos of nx upon n square. Then plus the derivative of this term is going to be 2 and the integration of this term minus sine of nx upon n2 and the limit is 0 to pi. Okay. So now we got this. So what we know about this sine term, so if you put n is equal to x is equal to pi, so it will become n pi, and if you put 0 it will become sine 0. So what we know is, since sine of n pi is equal to sine of 0 is equal to 0. Okay, so what it means, that is sine terms in both equation vanish at 0 and pi. Okay, and hence we get. So what do we get here? So we have an is equal to 2 upon pi. This minus and this minus will become plus. So we'll be having 2x cos of nx upon n square. And this limit is 0 to pi. So let's have this. What we'll get is 2 upon pi. This is 2 pi cos of n pi upon n square, and minus this is 0. Because when you put x is equal to 0, this term will turn out to be 0 and hence entire term goes 0. Now, what we know about cos of nx? So what we have is cos of n pi is equal to minus 1 raised to n, and hence we get an is equal to this 2, 2 will be there, 4, this pi will get cancelled, or I will simply write first 2 upon pi, 2 pi into minus 1 raised to n upon n. So this pi will get cancelled. This will be 4 minus 1 raised to n upon n square. And hence you get an is equal to 4 into minus 1 raised to n upon n square. So that's what we have equation 3. Now you can see we have calculated A0, we have calculated an, and so we are able to write the Fourier series for the given function. And hence we can write from equation 1, 2, and 3 we get. What we are able to get is f of x is equal to pi square by 3 plus 4 summation n running from 1 to infinity minus 1 raised to n upon n square, and here you have cos of nx. So this is how we are able to find the Fourier series for the function x square, that is pi square by 3 plus 4 summation n running from 1 to infinity minus 1 raised to n upon n square cos of n x. Okay. So this is the Fourier series for the function x square in the interval minus pi to pi. Okay. So that's how we are able to get this. So do you have any doubt in this example? Have you got this example properly? Do you have any doubt? Okay, that's great. Good. Okay, so if you don't have any doubt, let's go for the another example. Okay, so let's have the another example. And late, so find Fourier series expansion of f of x is equal to x cos x in uh, in minus pi to pi with period. So remember that if this information with period 2 pi given, that's okay. If it is not given, that's also okay, because the period is total length of the interval. Okay. So we go with the solution. Right. F of x is equal to x cos x be defined in minus pi to pi with period 2 pi, and hence L is equal to 2 pi. So L is equal to pi. Now we have to check this function whether it is going to be even or odd. So what do you know is, since x is odd, cos is going to be even. So the product of this odd function and this even function is going to be odd. Okay. So we have f of minus x is equal to minus x into cos of minus x. So what we know is, since cos of minus theta is equal to cos of theta, so it is minus x cos x, which is minus times x cos x, and that is minus times f of x. So we got f of minus x is equal to minus times f of x. Okay, so in examination you can identify this directly and go for it. Okay, so this is for your understanding. I'm writing here. Now, what do you know is, hence f of x is an odd function. So this is going to be an odd function, and hence if it is odd function, we know a0 is equal to an is equal to 0. So once we know a0 equal to an equal to 0, then we are able to write the Fourier series for this. Okay, so in case of even and odd function, please be careful. First, you have to identify the function. Then you have to write what is going to be 0, and after that you write the Fourier series. So we can have the Fourier series expansion for f of x is given as, what you can have is f of x is equal to summation n running from 1 to infinity. Now see, a0 is 0, an is 0, so there exists only bn, and here we'll be having sine of nx. Let it equation 1, where bn is equal to, this will be 2 upon pi integral 0 to pi f of x. Okay, first we'll write the formula and then we'll evaluate. So f of x sine of nx dx. Okay, so this is the formula. Now evaluate this. Hence we have bn is equal to 2 upon pi integral 0 to pi x cos x into sine of nx dx. Okay, so this I can write as 2 upon pi 0 to pi, and here we got x into sine of nx cos x and dx. So what we know is, since we know sine of a into cos of b is equal to half of sine of a plus b plus sine of a minus b. So let's use this formula and we get this is equal to 2 upon pi integral 0 to pi x into half sine of nx plus x plus sine of nx minus x and dx. This is equal to, this 2 will get cancelled, so we can cancel this 2 with this 2, and we have 1 upon pi 0 to pi x. Here we'll get sine of n plus 1x plus sine of n minus 1x dx. Okay. And now we have to use, this is bn. So here we get, this is u, and this entire term is b. So we need to use generalized by parts rule. So we say using generalize by parts rule. Okay. We get, what you are able to get is, see, bn is equal to 1 upon pi, 2 as it is. So we have integration of this term b. So it is minus cos of n plus 1x on n plus 1 minus cos of n minus 1x on n minus 1. And now minus the derivative of this term. So minus the derivative of this term and integration of this term. So it will become minus sine of n plus 1x on n plus 1 bracket square. This will be minus sine of n minus 1x on n minus 1 bracket square, and the limits are 0 to pi. Now we know these sine terms are going to be 0 at pi also and at 0 also. So we write here, since sine of n pi is equal to sine of 0 is equal to 0. Hence, we get this, both the terms will vanish at pi and 0 also. So we get bn is equal to 1 upon pi. This minus, if we can take out, I have this minus x, minus out, and this will become cos of n plus 1x upon n plus 1 minus, this is cos of n minus 1x upon n minus 1, and we have 0 to pi. Now let us apply these limits. So this is,
Sir, it will be plus inside.
yes,
Sir, it will be plus inside between the two terms.
So what happened?
So you've taken minus common, so it will be plus inside the bracket.
Yeah, this will become plus, correct. Okay, so minus 1 upon pi. Now apply the limit. This is pi. So if I use pi, then this will become pi, and you have cos of n plus 1 pi upon n plus 1 plus cos of n minus 1 pi upon n minus 1, and this minus 0. Because we have x here, so if I put x is equal to 0, everything will turn out to be 0. Now question is, what is the value of this cos of n plus or minus 1 pi? So what we know is cos of n plus or minus 1 pi, this is minus times minus 1 raised to n. Okay, so please be careful, don't make it plus, because this is minus 1 n times, and this is minus of minus 1 raised to n. Okay, so we have to be careful, and hence this is equal to minus 1 upon pi. This is pi. Here you have minus times minus 1 raised to n upon n plus 1 minus times minus 1 raised to n upon n minus 1. Okay, so for n plus 1 or n minus 1, this is going to be the same. Okay, and hence what we know is this pi will get cancelled. Okay, again I have minus, so this minus will multiply to this and this. So I will have this pi will get cancelled. Then it is minus 1 raised to n upon n plus 1 plus minus 1 raised to n upon n minus 1. So minus 1 raised to n is common, and hence here I will get 1 upon n plus 1 plus 1 upon n minus 1. So minus 1 raised to n, here we will be having n minus 1 plus n plus 1. Okay, so plus n plus 1 upon, you will be having this as n square minus 1. Now this 1 will get cancelled, and you will be having 2n minus 1 raised to n on n square minus 1. So you got dn is equal to, and hence dn is equal to 2n into minus 1 raised to n upon n square minus 1. Okay, this is equation 2. But we can see that this does not exist if n is equal to 1. Okay, so there is a trouble in evaluating b1 from this formula, because if n goes 1, then this will turn out to be 0, so this will be not defined, and hence this formula is applicable if n is not equal to. Okay, now we need to understand what happens if n is equal to 1. Okay, so let us see what happens if n is equal to 1. So let n is equal to 1, we have E1 is equal to 2 upon pi integral 0 to pi x cos x into sin x dx. Okay, so we have to evaluate this B1 separately, and hence B1 is equal to 2 upon pi integral 0 to pi. Here we have x, this is sin 2x by 2 dx. So this 2 will get cancelled, and you will have 1 upon pi integral 0 to pi x into sine of 2x dx. So again we have, this is u and this is v, so we have to use generalized by parts rule. So using generalized by parts we get. So what we are able to get here, see, this is v1 is equal to 1 upon pi. This x remains as it is, minus cos of 2x by 2, minus the derivative of x is 1. This is minus sine of 2x by 2 square, and we have 0 to pi. Now let us apply these values. So we get 1 upon pi. So if I apply pi, I'll be having minus pi cos of 2 pi by 2, minus minus plus sine of 2 pi by 4. Then minus, this term minus minus plus. So if I put 0, this will be 0. And this minus minus plus minus, we are using lower limit for minus. Sine of 0 is going to be 0. Anyhow, sine of 2 pi is also 0. So we get here 1 upon pi. This is minus pi. Cos of 2 pi is going to be 1. So minus pi by 2, and hence it is going to be minus half. So we get P1 is equal to minus half. So we got Bn, we got P1. So Bn here we have got, P1 we got here, and hence we are able to write down the Fourier series. So we can say from equation 1, 2, and 3, we have, so what we are having here, f of x is equal to minus 1 by 2 sine x plus. Okay, so what is the value of Bn we have calculated? See, this is the value of Bn we have calculated, so we can use it, and hence we can write twice summation n running from. Please be careful. For n is equal to 1, we have already evaluated this term. So n is running from 2 to infinity. So here we have n into minus 1 raised to n upon n square minus 1 into sine of nx. This is your Fourier series expansion for the function f of x that we have. Okay. So we got this as x cos x is equal to minus half sine x plus 2 summation n running from 1 to infinity n minus 1 raised to n on n square minus 1 sine of nx. So this way we are able to get the Fourier series expansion for the function f of x. So do you have any doubt in this example? So that's great. You are able to get, that's good. Okay. Let's have the another example for the Fourier series. So we go with the example. Find Fourier series expansion for f of x is equal to 4 minus x square in the interval 0 to 2. Okay. So we go with the solution. Wait, f of x is equal to 4 minus x square p defined in the interval 0 to 2. So we have L is equal to 2 and hence L is equal to 1. So please be careful now. The interval we have changed. The interval is going to be 0 to 2 now. So it is precisely 0 to 2L. So this interval is now 0 to 2L. Now we got L is equal to 1. And this interval is only positive. So there is no question of checking the function whether it is even or odd function. And hence the Fourier series expansion of f of x is given as. So what do you have? F of x is equal to a0 plus summation n running from 1 to infinity an, and we got here this is cos of. So please be careful. What is the Fourier series in the interval 0 to 2L? So f of x is equal to a0 plus summation n running from 1 to infinity an cos of n pi x by L plus summation n running from 1 to infinity then bn and sine of n pi x by L. So this is the formula for the Fourier series. Here already I have declared L is equal to 1. So we have to use this value here and hence we get this is going to be cos of n pi x plus summation n running from 1 to infinity bn sine of n pi x. So this is equation 1. And then accordingly we have to write the formula for this a0, an and bn. So we write where a0 is equal to 1 by 2 integral 0 to 2 f of x dx. An is equal to 1 by 1 integral 0 to 2 f of x cos of n pi x dx, and we have bn is equal to 1 upon 1 integral 0 to 2 f of x sine of n pi x dx. Okay, so this way we are able to write the formula for this Fourier series. Now let us evaluate this one by one. Okay, so first we have to consider a0. So a0 is 1 by 2 integral 0 to 2 4 minus x square dx. So this is going to be half 4x minus x cube by 3, and the limits are 0 to 2. So it is going to be half. So if I apply 2, I'll be having 8 minus 8 by 3. And if I apply 0, then this is 0 plus 0. So we got this half. 8 I can have outside, and I'll be having 1 minus 1 by 3. So this will become 4, and this will become 3 minus 1 by 3. So I'll be having 4 into 2 by 3. So it is 8 by 3 again. And this way we are able to get the value of a0. So we got the value of a0, which is 8 by 3. So let this equation 2. Okay. So we got a0. Now we have to find out what is an. So let us calculate an. Then we have an is equal to integral 0 to 2 4 minus x square cos of n pi x dx. Here this is going to be u, this is going to be v, and hence we have to use u into v rule. So we can say using generalized by parts we get. So what we are able to get here, see, we have an is equal to first term as this 4 minus x square, then the integration of this. So we got this is going to be sine of n pi x on n pi minus the derivative of this, so minus 2x, and here we'll get minus cos of n pi x upon n pi bracket square, and next you have plus, so the derivative of this term again minus 2, and the integration of this, so we're having minus sine of n pi x upon n pi cube, and the limit is 0 to 2. So what we know is, we can say since sine of, if I put 2, so it will become 2n pi. If I put 0, then it will become 0. So sine of 2n pi equal to sine of 0 is equal to 0. So that is the sine terms vanish at 0 and in of equation. Hence, we get. So what we are able to get is, see, there will be only this cosine term. So we have an is equal to, we can have this minus, and this minus, so it will become minus. I'll write this as 2x cos of n pi x upon n square pi square, and the limit is 0 to 2. So minus I have taken out, so it is 2 into 2 cos of 2n pi on n square pi square minus 0, because x is going to be 0, so this entire term is going to be 0. Then what we know is, since cos of n pi is equal to 1, so we get here an is equal to, so this is minus 4 upon n square pi square. All right, so an is equal to minus 4 upon n square pi square. So this is equation 3. So we got a0, we got an, let us go for, so now we have dn is equal to integral 0 to 2 4 minus x into sine of n pi x dx. So again, this is going to be u, this is going to be v. So we have to use u into v rule, and hence using generalize by parts rule, we get, okay. So Bn is equal to, we have here this u remains as it is 4 minus x square, then the integration minus cos of n pi x upon n pi plus the derivative is minus 2x, and this is minus sine of n pi x upon n pi bracket square. Next, the derivative is minus 2, and the integration is cos of n pi x upon n pi bracket square, and this is 0 to. So what we know again, since sine of 2n pi is equal to sine of 0 is equal to 0. So hence we have Bn is equal to, okay. So what Bn we are able to get here, this is minus 4 minus x square cos of n pi x upon n pi minus 2 cos of n pi x upon n pi cube, and the limit is 0 to 2. Apply the limit. If we apply this limit, this will be 4 minus 4, that is going to be 0, minus, here we will be having 2 cos of 2n pi, because x is going to be 2, upon n pi cube. Minus minus, this will become plus. So if you apply 0 here, then this will be 4 cos of 0 upon n pi. Minus minus plus, this is cos of 0 upon n pi cube. And now we know, since cos of 2n pi is equal to cos of 0 is equal to 1. So we can write Bn is equal to minus 2 upon n pi cube plus 4 upon n pi plus 2 upon n pi cube. This term and this term will get cancelled. So what remains is 4 upon n pi. And hence we get Bn is equal to 4 upon n pi. So once we get this value of Bn, let this equation 4. And now you can see we have got the value of A0. Okay, so we have calculated the value of A0. We have calculated the value of An. And now we have calculated the value of Bn. And hence we are able to write down the Fourier series. So we can say from equation 1, 2, 3, and 4, we get f of x is equal to 8 by 3. Okay. So what is the value of an we have calculated? Minus 4 upon n square pi square. So this we can write as minus 4 upon pi square minus 4 upon pi square summation n running from 1 to infinity 1 upon n square. This is cos of n pi x. Then here we have plus 4 upon pi summation n running from 1 to infinity 1 upon n, and this is sine of n pi x. Or we can write this is 4 minus x square is equal to 8 by 3 minus 4 upon pi square summation n running from 1 to infinity 1 upon n square cos of n pi x plus 4 upon pi. summation n running from 1 to infinity 1 by n and sine of n by x. And so this way we are able to get the Fourier series for the function 4 minus x square in the interval 0 to n. So that's what we are able to get. So do you have any doubt in this example or the examples that we have solved up to 8? Okay, that's great. So you don't have any doubt. Okay. Good.